Hello friends, welcome back in this video session of pharmaceutical analysis. In the previous session we have discussed the instrumentation of UV visible spectrophotometer. We have discussed the block diagram, schematic diagram, and what are the essential components of this UV visible spectrophotometer. We have also discussed the radiation sources, the types of radiation sources, and the wavelength selectors. So we have discussed various types of filters and various types of monochromators. So if you have not watched that video, the video link is given on the top of this video, so do watch that. Now in this today's session we will be discussing the remaining parts of this instrument. So after radiation source and wavelength selector, the monochromatic light is passed through the sample, and we need to hold the sample in a sample holder. So this is required for all kinds of spectroscopic work. So whether you are doing a spectrum mode, or whether you are doing a photometric mode or kinetic mode or whatever, so we need to keep our sample in the place so that the radiation can be passed and we can study the amount of light which is getting absorbed. So usually most of the samples are present in a solid form. Some may be present in the liquid, or it could be in a gaseous state. So based on the sample we can prepare the sample holder, right? So what we need to do, the cell or the cuvettes that hold the sample, that must be made up of material which will be transparent in the region which we are going to study. For example, let's say if I am using the visible radiation, so I have to use the material of construction in such a way that it is not going to absorb the radiations. For example, if I am using a glass material, so glass strongly absorb the UV light. So I cannot use the glass sample holder for samples whose measurement I want to done in the UV region. If you have liquid and gaseous samples, and if you want to measure their absorbance above 320 nanometer, then we should go for optically flat fused glass, which is a desirable one because they remain transparent above 320 nanometer. Then measurements below 320 nanometer require high quality fused silica cells, or we usually prefer the quartz material which remain transparent till 180 nanometer. So you can cover here most of your ultraviolet region ranging from 320 to 180 nanometer. So this is preferred one. Silica, fused silica and quartz material is preferred for such kind of analysis. Silicate glass can also be employed in the region of 350 to 2000 nanometer. Okay, and we can also use plastic containers, right, if we are interested in measuring the absorbance in the visible region. Even plastic is also transparent in the visible light. Then when we go for IR spectroscopy, we use the crystalline sodium chloride. This is commonly used as a construction of the cell or the sample holder in the IR region. Okay, so these are the things which we need to consider. The main idea is what kind of radiations we are using on the sample. So those radiations should not be absorbed by the sample holder. Okay, so based on that we have to select the sample holder. There are varieties of sample holders which are available in the market. So this is the one which is very commonly used. Okay, and this is made up of quartz. So quartz is a material which remain transparent throughout the ultraviolet and visible region. So if you are using a quartz as a material of construction for these cells or the cuvettes, then we can do our analysis very comfortably because the quartz is not going to absorb the radiations in the UV and visible region. Okay, and you can see, if you see carefully these quartz, right, there are 4 sides, right, and the two opposite sides are transparent and the remaining two sides are having the rough surface. Okay, so the transparent surface we have to put in the sample holder cavities in such a way that the light is going to pass through that. Okay, so the beam of light or the path of light should be exposed to this transparent part. Okay, and usually the path length or the distance of this particular cell is 10 mm, that is 1 centimeter. Okay, so most of the spectrophotometric measurements are carried out with the sample holder or the cuvette of size 1 centimeter in path length. Then for special applications or for certain kind of samples or methods, we may require the cells which have the size ranging from 1 to 50 mm. Okay, and when we go for biological samples where the amount of sample is very less, so we have these kinds of sample holders where it require very little amount of sample, you can see here, and the remaining part is it is filled part, right? It is having the material of construction, only the center part is vacant, and there we can fill our liquid sample which in the diluted form. So we need to take care of these cuvettes because they are made up of glass or the quartz, and this is very delicate and fragile material, right? So we have to handle them very carefully, and they are quite expensive. So the cost of one pair of sample cuvette that usually comes in a pair, so it is around 7,000 rupees, right? So we have to maintain them properly and we have to utilize it for particular work. So use of quartz cuvettes if you are doing UV region measurement, and you can use glass, plastic or even quartz if you are going for visible kind of measurements. Then nowadays we also have disposable cuvettes. These are recommended for colorimetric protein assays, since dyes are used in these estimations and they will definitely stain the cuvettes, and then these stains are very difficult to remove, right? So there is a problem with the cleaning, and if their stains are not getting removed, then we cannot use for other kind of samples. So these disposable cuvettes are nowadays very popularly used. Then we need to have the matched cuvettes, and they are manufactured to absorb the light identically. So whenever we purchase the cuvettes, we purchase in a pair, right? So that we can match them identically and we will get the results without the error. Then do not touch the base of the cuvettes or sides through which the light is getting directed. Okay, so I told you the transparent surface and semi transparent surface, so we should handle the cuvettes with the semi transparent surface. Then we should not scratch the cuvettes. Okay, so the scratches may scatter the radiation, it may obstruct the radiation path, and that's why we should not put the scratches on the cuvettes, and we should store them in proper store case so that it will not have the scratch, right? We should not put them into a wire racks, and we have to clean them with the tissue papers, right? So we should not use brush or any kind of abrasive because it will create these scratches. Then we should not allow samples to sit in the cuvette for long time, otherwise it again will make difficulty to remove these kind of samples. Then we should make sure that the cuvettes is properly aligned in the spectrophotometer. Okay, so we have to properly push the cuvettes in the particular cavity in the instrument, that we should take care, and we have to use properly cleaned cuvettes. Okay, so most of the times we are using repeatedly the same cuvettes for the colorless kind of samples, so we should clean them properly, we should dry properly with the tissue papers, and we have to hold them in a proper case so that we can use it for longer time. And then we have to wash the cuvettes immediately whenever your work is done, so that we can use it again and again. So this is the chart come table which gives an idea about what kind of construction material we can use for constructing the cells or the sample holders. So when we talk about the lithium fluoride, so lithium fluoride is transparent in the region of vacuum UV, UV visible, near IR and even IR to some extent. Then you can see the fused silica or the quartz, so that is totally transparent in the UV visible and even in the near IR region. So that is why the quartz or the fused silica is the preferred material for making the sample holders for UV visible spectrophotometer. Then we have the Corex glass, then silicate glass, they are also used to some extent, but they will be mainly used in the visible region. Then I told you the sodium chloride, then potassium bromide, they are used in this IR sample holders. Okay, and then some others are also there, but the popularly used is quartz or fused silica, and glass can also be used, silicate glass to some extent. Okay, so that is all about the sample holders. Then next is the radiation detectors. So ideally we have the detector, and the role of the detector is it should sense, it should detect the amount of light which is getting transmitted from the sample. Okay, so it should either give the percent transmittance or it should give the amount of light which has been absorbed in a logarithmic scale. So what are the properties of ideal detectors? So for accurate determination of our sample, precise determination of light intensities is must. Okay, so photoelectric detectors are most commonly used for these kinds of purpose. So the detector should have high sensitivity, it should give high signal to noise ratio. So noise is something which is not required, it is something which we do not require, and the signal is the kind of information which is coming from the analyte, right. So when we take the signal to noise ratio, it should be high, right. So the detector should give the signal in such a way that the ratio of signal to noise ratio should be high. Then constant response over a considerable range of wavelength is good, and then it should exhibit a fast response time and zero output signal in the absence of illumination. So these are certain ideal properties what we can expect from the detector to consider it as an ideal detector. So there are basically two types of detectors, one which responds to the photons and other one which responds to the heat. All photon responding detectors, we call it as photoelectric or quantum detectors. Okay, because energy is usually quantized, so we are referring these kind of detectors as a quantum detectors, or they are referred as a photoelectric detectors. So they have an active surface capable of absorbing the radiation which cause emission of electrons and development of photocurrent. In some cases the radiation promotes electron into conduction bands, that is enhanced conductivity, which we refer it as photoconductivity detectors. So there are several types of detectors which we can categorize under photon detectors or the quantum detectors. So first, which is very popularly used, that we refer it as a photovoltaic cell. So photovoltaic cell is nothing but, in this the radiant energy generates a current at the interface of semiconductor layer and the metal. When we see the second type, phototubes, so in these phototubes radiation causes emission of electrons from a photosensitive solid surface, which we refer it as a photoemissive surface also, and this is the basis of phototubes. Third is a photomultiplier tubes, which we refer it as a PMT, photomultiplier tubes. So these contains a photoemissive surface as well as several additional surfaces that emits a cascade of electrons on struck by electron from photosensitive area. So this is basically multiplying the emissive electrons, and then the signal will be amplified in this photomultiplier tube in a better way. Then photoconductivity detector is the absorption of radiation by semiconductors which produces electrons and holes, thus leading to enhanced conductivity. Silicon photodiodes, in which photons increase the conductance across a reversed biased PN junction. So, this is the brief idea about the several types of photon or quantum detectors. So, first type of detector under the photo cell, that is barrier layer cell, or it is also referred as a photovoltaic cell. So, this basically gives the current which is directly proportional to the light intensity. So, we can see the construction of this particular photovoltaic cell, right. So, you can see what we do here, we have the selenium, and this selenium is sandwiched between the thin layer of silver and iron. So, you can see iron is at the bottom, then on the top we have the silver, thin layer of silver, and in between silver and iron we can see there is a selenium, okay, and these are connected to an electric circuit or the photocell having negative and positive terminal. Okay, so we can see here the selenium, this acts as a semiconducting layer which is deposited on the iron or copper cathode. So, in this diagram we have taken iron, and this iron is acting as the cathode because it has a negative sign here, and then the metallic layer, that is the gold or silver, which is acting as the anode, that is connected to the negative terminal. So, when the radiation reaches the semiconductor, how it reaches the semiconductor? This is maintained in a vacuum. You can see here this cell is closed, and on the top we have thin layer of silver, and above the thin layer of silver we have a transparent glass plate. So, the entire inner environment is present in a vacuum. So, when the radiation from the sample enters through this glass to the selenium layer, through this silver layer, right, what it does, it reaches to the semiconductor, and then covalent bonds are broken, which results into conduction of electrons and the holes. So, the electrons flow towards the metallic layer, that is the anode, and the holes flow towards the base of the semiconductor, that is cathode. So, the electrons then flow through the circuit, and this will result in a current which is directly proportional to the power of the radiation, right. So, this is how we can get the amount of light which is getting transmitted or coming out of the sample, because here the current which is flowing through this circuit having positive and negative terminal, that is directly proportional to the power of the radiation. So, these kind of barrier layer cells or photovoltaic cells are usually useful in between 380 to 780 nanometer range. That means they are mainly useful in the visible radiations. So, they are cheap and they are rugged and most commonly used in the portable devices. Okay. So, that is the use of barrier layer or photovoltaic cell. Then next type is a phototube, or these are also called as a vacuum phototube, because the phototube's inner environment is maintained in a vacuum. So, these are consisting semi-cylindrical cathode and a wire which is acting as an anode and sealed inside an evacuated transparent envelope. Okay. So, that is why it is called as a vacuum phototube. The concave surface of the electrode supports a layer of photoemissive material that tends to emit electron when we irradiate them. Okay. So, irradiation with the help of emitting radiations or the transferring radiations from the sample, the emitted electrons then flow to the wire anode, generating a photocurrent which will be equal to the amount of radiation falling on it, and this will give a potential applied across the two electrodes, that is cathode and anode, and this phototube is generally operates at 90 volt, and they produces a small dark current that results from thermally inducted electron emission. So, we can understand this with the help of this simple diagram. So, this is a semi cylindrical cathode, right, and you can see this cavity. So this particular semi-cylindrical cavity, which we are referring it as a cathode, it have the material, photoemissive material, which is coated on this semi-cylindrical cathode. Okay, so these photoemissive material may be a gallium or the arsenium. So that is coated on this particular photoemissive cathode, right? And we have a wire, you can see the wire here, which is acting as a anode, right? And then they are connected to an electrical circuit having the positive and negative terminal. So by applying a potential across the cathode and anode, the electrons will flow from cathode to anode, resulting in a photocurrent. So when the electron comes from your radiation, so the light which is coming out of the sample holder, right, so that will be projected towards this detector. So light will give the electrons are falling here on the cathode, and then it will move towards the anode and it will generate the current, right, and this current is directly proportional to the amount of intensity of the radiation, right. So this is how we can detect the transmitted radiations or the amount of radiation which has been absorbed by the sample with the help of phototube or the vacuum phototube. Then next is a photomultiplier tube, which we abbreviate as PMT. So this is used for measurement of low radiant power. So whenever there is a low radiant power, these kind of radiations will be difficult to detect by the barrier layer cell and photo tube. So we need to use the photomultiplier tube, which actually multiply or amplify the signal. So the photocathode surface is similar in composition to the surface of the phototube, right. Here the tube contains additional electrodes. So this is the main difference between the phototube and the photomultiplier tube. So here we have additional electrodes. In earlier case there was only one electrode, right. So here we have the 9 dinodes, right, which are acting as an electrode. In earlier case of phototube there was only one dynode or one electrode, right. So if you have low radiant power in phototube, it won't be detected, but here what we are doing, we are using 9 electrodes in the form of dinodes. So the first dynode is maintained at potential of 90 volt, then electrons are accelerated towards it on striking of photon, and then electrons are accelerated towards the second dynode. So these 9 dinodes are arranged in such a way that when the light strike on the first dynode, it will reflect back into the second, then in second it will get multiplied and it will go into the third, then again third it will get multiplied and it will go into a fourth one, and so on. So every time it is getting striked on the dynode, it will be getting multiplied and the low radiant power will be getting amplified and will get detected in the detector. So this process is repeated 9 times, and this is amplifying the signal, I told you, into the power of 10 raised to 6 to 10 raised to 7. So that many times the signal will be amplified. So these are finally collected to the anode and the current then electronically amplified and measured. So they are highly sensitive to UV and visible radiation, and they give fast responses. So these performance can be enhanced by cooling, because usually they will get heat up. So because of that we can improvise the performance by having a cooling system, and these cannot be used for measuring the intense light, okay, because that is not required. Intense light you can easily monitor or detect by using a barrier layer cell or photovoltaic cell, and if you are using intense light, in this case it will produce very high heat, and that will create a problem to the photomultiplier tube. So this is basically what the construction of photomultiplier tube is. So you can see the incoming photon or the light which is coming out of the sample is strike here on the first dynode, then from first dynode it is going to the second dynode, then the light is amplified into let us say 2 intensities, then again from here to right, and then again it is getting multiplied here and so on. So you can see as it proceeds from one dynode to second and second to third and third to fourth and so on, the signal is getting amplified, and you can see here it has a very good intense signal which can be detected by the photomultiplier tube. Okay, so this is actually how the photomultiplier tube looks like, and this is another way of representing the photomultiplier tube. Okay, so you can see here there are focusing grills, and the incident light is coming here 0, and then it is striking to the first dynode, then it is going to the second dynode, and then third, and then fourth, and so on. Okay, so there are 9 dynodes can be represented here in this diagram, right. So this is all about the detector. Then we have the signal processor and readout system. So the signal processing include amplification of electric signal and alteration of signal from DC to AC, etc. So they are also required to perform mathematical operation on signal as differentiation, integration, or conversion to a logarithmic values, and then readout unit convert the electrical signal to a readable form. Readout devices include digital meter, scale of potentiometer, recorders, and cathode ray tubes. It also include fiber optics or light pipes to flow the light from one part to the another. So this is basically an instrumentation engineering, right. We need not to go into details of that. So just brief overview of the readout and signal processor system. So whatever signal has been collected from the detector, which will be converted into a understandable or the readout format which we can understand. So this is all about the instrumentation of UV visible spectrophotometer. Now next is, there are basically two types of UV visible spectrophotometer. So earlier days we used to have the single beam spectrophotometer, or it is referred as a single beam instrument. So these can be either single channel or scanning instruments. Okay, so here you can see we have the light source, right, and then it will have a certain intensity, let's say at nu, and then we have the filter or the monochromator which are converting the polychromatic light to a monochromatic light, and then we have the shutter, right. So to have a particular kind of light which is focused here, and then we have a reference cell and the sample cell. So actually here we are using only one beam of light, so one at a time we can pass the light into a reference cell or to a sample cell. So let us say if I am passing the light through a reference cell, that is your blank, and then we have a photo detector, it will detect the percent transmittance or the absorbance, and then we will get certain absorbance. Then afterwards what we can do, we can take our sample and then we can record the absorbance, right, and then we can subtract the reading of sample and reading of reference, that is absorbance of sample and absorbance of reference, and the subtracted reading will be the actual reading or the actual absorbance of the analyte, right. So this is what we used to do in single beam instrument. So there is a 0% transmittance which we need to set with the shutter in the beam path, and 100% transmittance we need to set with reference in the beam path, and then we can do the measurement with the sample in the beam path. Okay, and nowadays very frequently and popularly we are using a double beam spectrophotometer or double beam instrument. So in this case what we are doing, you can see here the light source which is emitting the radiation in a polychromatic way. All these polychromatic radiations are focused through the slit 1, this is also called as an entrance slit, and then we have a diffraction gratings. So these diffraction gratings are nothing but the monochromators, right. So these monochromators are actually rotating monochromators. So by rotating these monochromators we can select the particular wavelength of light, and we can destroy or restrict the unwanted wavelength of light, and then the selected wavelength of light can be focused to the slit 2, which is again getting filtered to a narrow bandwidth, and then you can see it is falling to the mirror 2. Then from mirror 2 we have the half mirror. So mirror 2 is focusing the light to the half mirror. So this half mirror is also referred as a chopper, and this chopper or the half mirror, what it does, the intensity of this light which is indicated in the red, so this is splitted or it is chopped into two equal intensities. Okay, so this particular beam is splitted into two parts, right, of equal intensity. So the intensity of this blue and intensity of this pink is same. Only for our understanding we have indicated in two colors, but these two colors represent two beams of equal intensity, right. It have the same bandwidth, right. And then one beam of light is passing to mirror 4, and then it will be going to a reference sample holder or the reference cuvette, right. And another beam of light which is having the same intensity as that of the purple light, right, it has been passed to the another mirror, mirror 3, and then it will be sent to the sample cuvette. So simultaneously we have the two sample holders, one holding the blank or the reference and other holding the sample. So the beam which is coming out of the radiation source, which has been filtered by the monochromator, have been splitted into two beams of equal intensity, one beam passing through the reference and other beam passing through the sample. And then we are having two detectors to detect the amount of light transmitted from the reference and the amount of light transmitted by the sample, and then this we refer it as I0. So I0 is nothing but the incident radiation and I is the radiation which is getting transmitted from the sample. So we have a readout system, and through the help of the signal processor, what we can do, automatically the instrument will give the subtracted reading. So instrument will nullify the effect of this blank or the reference, and it will give the absorbance of only your sample. So you need not to manually record the absorbance of blank and then record the absorbance of sample and then calculate manually the difference. So that is not required in the double beam spectrophotometer. So it automatically record the difference, and the absorbance what we are observing, that will be the absorbance given by the analyte. Okay. So this is the advantage of double beam spectrophotometer over the single beam spectrophotometer. So here what is required, we need to have the matched quartz cuvettes. Okay, so what I have told you when we have discussed the sample holder, we have to have a pair of sample holders or pair of quartz, and these pairs have been matched with each other, okay, to avoid the error. And the sample what we are taking to record the absorbance, as Beers-Lambert's law is obeyed only in the dilute solutions. So we need to prepare a sample solution of concentration 10 raised to power of -5 molar. So that is the desirable concentration of our sample what we are going to use in the UV visible spectrophotometer. Then the system protects the PM tube, photomultiplier tube, from the stray radiations or the light. Then deuterium lamp is required when you are using the ultraviolet region of light, and tungsten lamp is required when you are performing in the visible region. Okay, and this double beam makes the difference technique, right. So there are a lot of analytical methods based on UV spectroscopy. So you can use a difference spectroscopy, where we need to have a difference in absorbance, that is delta A. So that can be easily found by using this double beam spectrophotometer. Okay, so that is all about the UV instrumentation and the differentiation between single beam and double beam spectrophotometer. Thank you for watching it.